Okay, 3-2, day 2. So you guys are going to be starting off with just a little activity here. I'd like you on your calculator to graph the function y equals absolute value x plus 2. Or you could probably even tell me what that looks like, right? It's just a very familiar graph, shifted up to. But let's get it on the screen. We're going to do some zooming in. I'm going to try to convince you something. And let's try to zoom in several times at the point 02. I'll do the same while you're working on that. So remember, you can find absolute value under math numbers. And if you have it on Zoom Standard like I do, it looks like that, right? Not a foreign graph. We know this graph. Okay, let's zoom in. Remember, when you zoom in on a TI-84 at least, you can choose where you wish to zoom. So when you first press zoom in, it's just kind of waiting there blinking at the origin. You can barely see him there, little cursor. Move that thing up to roughly 0, 2 and press enter, and it will zoom in on that particular point. Okay, it looks like the cursor is still blinking at 0, 2, so I'm going to zoom in again. Press enter. I'll do it a third time. You might say, what in the world are you doing, Mr. Shore? Well, I'm noticing something. It seems like no matter how far I zoom in, what I have here is a what? What do we call this? We talked about it yesterday. A corner. Yeah, it's a corner. Right? So you might say, yeah, Mr. Shore, we knew that. The absolute value function has a corner. You showed us that yesterday. You shifted it up to. It still has a corner. If you check your window, like right now, I'm already looking just between negative 0.15 and positive 0.15. So I'm really very, very zoomed in. And you know what a corner looks like when you zoom in really, 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 really close and look at it really close? It looks like a corner. It looks like a corner. So here's my question. If I keep zooming in, will it continue to look like a corner? Yes, it will. Okay, now, let's go back to Zoom Standard. And now we're going to go in and change the function. Okay? So the function now is the square root of x squared plus 0.001 plus 1.99. So I know it's awkward, but let's get that one up on the screen now. X squared plus 0.001 and then plus 1.99. What do you notice right off the bat? It's the same graph. Or is it? It's a different function, right? Let's zoom in. Okay, so we're zooming in at 0, 2 still. Move your cursor up there, roughly. Okay. Okay. Looks like the same graph. Let's zoom in again. Okay. Should we keep doing this? Yes, we should. Ooh, interesting. On my third zoom, what do I notice? That's not a corner. In fact, it's starting to look differentiable there. If this were a roller coaster ride, I wouldn't be too jolted as we pass through that point, right? Maybe a little bit, but it wouldn't be a sharp jolt. Zoom in again. Sorry, I'm losing my center of zoom here. Move this up. Very interesting. That's not a corner. Okay, so my first observation is that this is a differentiable point. X equals 0 is differentiable. That's my first observation. Okay? We'll go back and write down our observations in a minute. I'm going to zoom in one more time because it's starting to look kind of interesting. This is something I noticed in high school when I got my Casio graphing calculator back in the day. And I remember zooming in and zooming in and zooming in and suddenly realizing that it doesn't even look like a curve anymore. What is it starting to look like? It's starting to look like a line. Okay? So I'm kind of noticing two things here. One is, it's definitely not a corner. And it's starting to look very, very straight as I zoom in. I'm wondering what my window is right now. I'm going to click window and see. Really? That's my window? -6 and +6? Okay. Well, all right. Between -6 and +6, it's already looking much, much like a corner. I like a non-corner. Okay. So I'm going to go back and write down some observations here, and then we'll talk about this a little bit more. So on the first graph, the first thing we noticed was that we had a corner, right? There is a true corner at x equals 0, right? And we can see that no matter how far you zoom in, a corner is a corner. So I'll just put no matter how far we zoom in. F is not differentiable at x equals 0. Right? Okay? In the second graph, what I noticed was the graph is differentiable, right? So F is differentiable at x equals 0. It is not a corner at all, even though it appeared to be. And as we zoom in, on a point that is differentiable, a point where F is differentiable, the graph of F appears linear. Okay, I wish I could tell you just how much history went into that, learning that. But understand this, the early founders of calculus understood that if a graph does have a slope, then as you look at it closer and closer, all graphs are straight. Okay? Now there are some really funky graphs that are so jagged that if you zoom in on them, there is never straightness. You guys know what a fractal is? You guys know what a fractal is? Ever heard of a fractal? Okay. Well, a fractal is like a pattern that repeats itself indefinitely. So maybe you've seen some online. You should check Google Images for fractals. They're really, really beautiful. So you can see these pictures, and there are spots on there that look nice and round. When you zoom in on them, you see, oh no, that's not round at all, if you looked at them up close. But anyway. There's a function in your book on one of the pages, and no matter how far you zoom in, not one point on that graph is straight. It's so jagged and so messed up, there's not even one differentiable point on the entire graph. Interesting. But on this graph, it was differentiable at 0, wasn't it? Okay, and then some of these early guys, they realized that every curve straightens out as you're looking close to it. Okay? So that's pretty interesting. We have actually seen this before, but we didn't realize it at the time. Do you remember when we wrote down that sine x over x has a limit of 1 as x goes to 0? Let's write that down just one more time. Let's just look at that from this standpoint. When we wrote this, the first week of school, I asked you to memorize it because we didn't have a proof for it. And you had to use it on the test, even though you didn't have proof for it. But what exactly does this mean? Well, if you're looking at the graph of sine x over x, it means that on either side of 0, the limit is 1, right? And if you actually zoom in on the point 0, 1, you'll find it's actually empty, right? You guys understand that? Okay. But there's another way of thinking about this. Another way of thinking about this is when x is very small, sine x and x are approximately the same. Therefore, we get a ratio of 1. It's a totally different way of looking at it. But think of it this way. You've seen the graph of sine x before, right? And you've certainly seen the graph of y equals x. So this is y equals sine x. And this is y equals x. One way of interpreting this is to say that when you are near 0, these two graphs are virtually indistinguishable. You can't tell the difference between them. You guys see what I'm saying? Okay. So, that's one way of thinking about it. In other words, if you zoom in to sine x near the origin, it looks like you're looking at the line y equals x. And this is true for all differential curves. It always looks like a straight line with some equation as you zoom in. Okay, let's move on though. We don't want to get too caught up in that. Here's our next activity. So what we want to do now is try and figure out what kind of non-differentiable point these 4 situations give us. Okay, so can we refresh our 4 cases from yesterday? Does anybody have them memorized? There are 4 types of non-differentiable points. Remember what they were, Kevin? Corner. What was the other one? Cusp. Yeah, if f is not continuous, then we have non-differentiable point. That's kind of the 4th one. There's one more. Yeah, if a tangent line can be drawn, but it is vertical, then that's the 4th case, you can say, of non-differentiable point. So we're going to just run through these, and we're going to try really hard not to graph them. Okay? On the calculator. We're going to try to use our background with secant x and tan x and all that, and see if we can sort of roughly sketch a graph. Okay, so what does secant x look like? Do you guys remember what the graph looks like for that thing? Yeah, so some people, the way some people memorized that graph was if you draw yourself a cosine graph, right, you can find your secant graph just by building onto the top of it like that, and then going like that. You guys learn it that way? Okay. Well, in any case, oops, I meant to erase. Your secant graph looks like this. Okay, now we're not interested in the whole thing. We're actually only interested in the part between negative pi over 2 and 0. So that's actually just between the first asymptote on the left and the y-axis. Okay? All right, so right there. What does tan x plus 1 look like? Okay, so you probably remember the graph of tan x, right? It's just going to be shifted up 1, not left 1. Left 1 would look like this, ladies and gentlemen. That would be left 1. Right? It's up 1. And tan x, if you recall, it's on my wall behind me too. Tan x looks like this. Maybe you remember that it looks sort of like y equals x cubed. Okay? Okay, so I have a question. If we shift it up 1, it's going to look like this. If I were to draw that here on my y-axis, because that's what it's asking me to do, wouldn't that just look like this then? boy, it's awfully hard to tell if that's differentiable or not, isn't it? So you need to know something about tan x. It is not like x cubed. Okay, how many of you memorized that tan x looks something kind of like x cubed? Okay, that's kind of how I remember it too. But here is a key difference between x cubed and tan x. You can see it in the picture behind me. Notice that all the polynomial power functions pass through the origin, and they all have a horizontal tangent line at the origin. See that? They all go up, they completely flatten out, and then they keep going up, except y equals x. But like x cubed, x to the fifth, x to the seventh, they all go up into the origin, flatten out, and then leave the origin. But tan x isn't like that. Tan x never flattens out. Do you remember the first week of school we also did this limit? Do you guys remember doing this limit the first week of school? Some of you. Do you remember what it came out to be? Okay, you'd have to look through your notes, but it's 1 also, just like sine x over x. In other words, what we're saying is tan x and y equals x are virtually indistinguishable near 0. And what is the slope of y equals x? Come on, guys. What's the slope of y equals 1x? 1. So tangent does not have a flat spot in the middle. It has a slope of 1 in the middle at 0, see? It has an instantaneous slope of 1. So what I'm saying is, when you draw this, you've got to be really careful. It's actually more like this. Okay, if you're coming in from the left, the tangent lines are getting closer to 0 slope. But if you're coming in from the right, the tangent lines are getting closer to a slope of 1. In other words, the left-hand derivative is 0 and the right-hand derivative is 1. Okay, let's write that down. We talked about one-sided derivatives the other day. The LHD is 0. That's the slope of the little black dashes there. And the right-hand derivative is 1. So you tell me, is it a corner, or is it a cusp, or is it a point of discontinuity, or is it a vertical tangent? It's a corner. So whenever LHD and RHD come out to numbers, okay, and they're different numbers, we have a corner. All right, so this one's a corner. Your justification's over here. LHD is not equal to RHD. Let's look at x to the 1/3. So it's getting really tempting to grab our calculators. Really tempting. Now, if you don't know a graph, right, you have an option. What my Algebra 2 students do is they just draw a table. First time they've ever made the graph for that or whatever, they would just make a table, XY table. But you guys have a lot more tricks up your sleeve. So if you don't know what x to the 1/3 looks like, couldn't you just ask yourself what y equals x cubed would look like? This, after all, is the inverse function. Listen, if you know what x cubed looks like, then you know what x to the 1/3 looks like. What does x cubed look like? We just talked about it, right? So what does x to the 1/3 look like? Right? Isn't it true that when you do an inverse function, all you do is just reflect over the y equals x line? So you might know twice as many graphs as you thought. If you know x cubed, you also know the graph for cube root of x, right? If you know x to the 5th graph, you know the 5th root of x graph. It's just the inverse. Okay, you tell me, looking at that red one, what's going on at the origin there? Is that a cusp? Is that a corner? It's red there, that red graph. That's the vertical tangent case. The vertical tangent case. There is a tangent line that can be drawn at the origin, but unfortunately it has no slope. So the black graph, x cubed, had a horizontal tangent at the origin, right? Therefore, its inverse would have a vertical tangent at the origin. Okay, so everything I'm saying is very meaningful, and if you get a chance to go back and listen to this video, some of these comments are really important. I'll try to keep saying them throughout the year, but we'll see that idea again later in chapter 3. So you do know the graph of that. That's definitely a vertical tangent case. Vertical tangent at x equals 0. All right, so that's the answer for part B. What happens when you try to graph x to the 2/3? Don't grab the graphing calculator. You can think of this as x to the 1/3 squared. What happens to a number when you square it? What happens to a number when you square it? Typically gets bigger unless it's a decimal, then it gets smaller. What happens to a negative number when you square it? It becomes positive, right? So the difference between this graph and the previous graph is that there cannot be anything in the lower quadrants. Because y is clearly going to be 0 or greater. Just by the fact that we're squaring means we're not going to get any negatives for range. So actually what happens is it also does get steeper in most parts of the graph. And so you can kind of just roughly sketch this. But imagine taking that red one and sort of steepening it, but also keeping everything out of the lower quadrants. It's going to look like this. I like to think of this as the seagull graph. And I've memorized many of these because they're so used on the AP test. We use them so much. So you tell me, what is that thing? What kind of point of non-differentiability is that? That's a cusp. Sorry, it's getting kind of messy here. Okay, so we have a cusp at x equals 0. If you had to peek at your graphic calculator for that last one, that's okay. Okay, and then int x, that one you should know. But the function looks like this. I don't want to draw too much because we're only interested in x equals 0 if you read the instructions. This is the easiest one of all. Why is this function not differentiable at x equals 0? It's not even continuous. Right. So f is not continuous at x equals 0. So you'll be doing this tonight, okay? Some of this stuff. Try not to use your graphing calculator tonight. Tomorrow night you'll get a chance to use it a lot. Yeah?
For part A, can you go over how you knew the left-hand and right-hand derivatives?
I knew them from my knowledge of these graphs. Okay? So if you take a look, let me pause this recording. Okay. Let's go on. How does a calculator find a derivative? Can a calculator find a derivative? If you type into your calculator derivative of x squared, will it say 2x? If you have a TI-89, it will. If your TI Inspire has the CALC processor, it will. But if you're like most of us and you have just a TI-84, it will not. It will not be able to say that the derivative of x squared is 2x. What it can do is find a derivative at a value for you. For example, if you wanted to find the derivative of x squared at x equals 5, it will do that. So the first thing you need to understand is it does not understand derivative rules. So all those tricks Mr. Lynch taught you, it does not understand that. It's not that smart, unless it's a TI-89, then it really is that smart. It can only find the derivative at a point. You have to provide it a value. Okay? All right, so that's the first thing you need to know about your calculator. The second thing is, it does not actually understand. Oh, that's the same thing I just had. The calculator actually is just using a formula to find the average rate of change between 2 points, and for those points, it might choose the number you gave it plus 1/1000th, and the number you gave it minus 1/1000th. Okay? For example, if you tell the calculator to find the slope at 2, it will use 2.001 and 1.999, and it'll just do an average rate of change calculation. And it just figures, well, that's close enough to IRR. Such a small interval, it would come out so close to the slope of that tangent line anyway. That's what the designers of the calculator were thinking. So like I was saying, if you chose x equals 2 as a place to find the derivative, it would probably use 1.999 and 2.001. And it would follow this calculation down here. It'll take f of 2.001 and f of 1.999 and then subtract them, and then divide by 2.001 minus 1.999. In other words, 0.02 on the bottom here. So here's what the calculator uses. It takes the value you give it, and it calculates this. Then it calculates this. And then it divides by 0.02. Let me see if I can explain that graphically. Imagine you gave it instructions to find the derivative of this curve at x equals 2. It doesn't know how to find a derivative. But what it can do is find the average rate of change between 1.999 and 2.001. See? If it finds this slope for you, you should be pretty satisfied with that. We know the tangent line is actually not exactly the same thing, but gosh, they're awfully close. Would you agree? Okay, so understand that your calculator is going to find the slope of that red line, not the true tangent line slope. Okay? So I'd like you to now turn on your calculator, and we're going to make it do this. So we're going to have the calculator take the derivative of 2x squared minus 2x at x equals 5. Don't worry about the part where it says h equals 0.001. Okay? Let's just get the calculator to do our derivative for us. All right, so turn on your calculator. Go to the home screen. By the way, this is not optional or luxury. On the AP test, they've designed it where if you don't do this, you will miss lots of problems. So you have to learn how to do derivatives on your calculator. Before I type the function, I actually want to press Math 8. This is what I see. Math 8. And I'm going to type the function, 2x squared, sorry, minus 2x. Okay, now I need to tell the calculator what my independent variable is. Well, that would be x. And then I need to tell it that I want to do the derivative at 5. So I press comma x comma 5. The first comma x tells the calculator what the independent variable is. The second comma 5 tells the calculator where to find the slope. And you can press enter. Oh, by the way, make sure you're using this button for your x, not the alpha x. Okay. And I wish it would give me the actual derivative, but it can't. But it can tell me the slope of that tangent line is 18. This is the derivative of 2x squared minus 2x at x equals 5. That's pretty cool, right? So how did the calculator do it? Here's roughly what the programmers programmed it to do. So watch close. You said 5. So the calculator decides to use f of 5.001 minus f of 4.999 all over 5.001 minus 4.999. It's just an average rate of change calculation. It calculates 2 times 5.001 squared minus 2 times 5.001. From that, it subtracts 2 times 4.999 squared minus 2 times 4.999 and divides by 0.002. All right, so if you type this in, it will come out to 18. This is what the calculator is doing. There's no limbo. It's not a true derivative. It's an average rate of change on a very tight interval. Okay? You have to do this by hand a couple times tonight at home. It's actually tomorrow night's homework or the day ahead of lessons. So you actually write this and punch it in and see what happens. And then you can verify it using these buttons. What were those buttons again? Just in case you didn't find them. Oh, I showed you on the screen, right? That's what I had. There it is. So you press Math 8, you get this end deriv, and then you type in the function, comma x, comma 5. Okay, so I just want to warn you about something real quick. What do you suppose the calculator would do if you told it to find the derivative of absolute value of x at the origin? We know there's a corner. That's funny, my bell rang 2 minutes early. What's going to happen? We know it's supposed to come out to no solution, right? But you know what the TI is going to do? The TI is going to pick this point, and it's going to find the slope. It's going to find the slope to be 0. It's not differentiable. See that the graphing calculator will report a slope across a non-differentiable point when it should be stating that it is not differentiable. Okay, so that's kind of a little glitch there, isn't it? So you have to be smarter than your calculator on those ones. Okay, a calculator can also graph the derivative of a function. Here's how you graph a derivative on your calculator. First, you enter your function as y1, and then under y2, you want to type this expression, inderiv of parentheses y1 comma x comma x. This x is declaring the independent variable, which of course is x, and this is just telling the calculator not to pick one particular value of x, but to run through the real numbers as best it can in the window you've chosen under the window tab. Okay, so this means all x. Again, it's not going to do every x, but it will calculate for various x's within the window that you have chosen. Okay, if you have the newest operating system for TI-84, you have a slightly different look when you press Math 8. It gives you some boxes to fill in. You can just fill it in like this. Use the X button. Some of the older TI-84s can be upgraded to the newer operating system. You'll have to research that online. And you have to have a connection cable to your computer. Or you have to connect to another friend's calculator and dump their operating system onto yours. Okay, let's just see what the calculator will do with y equals x to the 2/3 for the derivative graph. So let's take a look at our calculator here. Okay, so we're going to go into here and we're going to enter in x to the 2/3. X to the 2/3 is the graph I mentioned earlier. It looks like a seagull. Okay, so you can look at it real quick if you'd like. I forgot to do a zoom standard here. Let's do a zoom standard. Here's your little seagull graph. Okay, and now we're going to try and graph the derivative. Alright, so let's see what that derivative graph looks like. Okay, so now we'll go to y equals, and under the second line we'll press Math 8. And to get that function there as our function to differentiate, that means take the derivative, we're going to do either retype it, or you can press variables, go over here to y variables, and right here the first option says functions, click functions, and there it is right there, y1. So this is the function you had typed on the previous line in the function editor. And then you do comma x, that means your independent variable is x, and then you do comma x, this means you want it to use all the values of x in the window you've selected. Okay, so I think I have zoom standard, so it's going to plug in a bunch of numbers from -10 to +10 or something. Anyway, let's see what it does with this. And let's do one more thing. Let's make it thick. So let's go over here and click on this little symbol to make it thick. Just press it once. If you press it too many times, just keep pressing it until it goes back to the dark bold there. Okay, so here comes the derivative graph. You can see that the slopes of the tangent lines are being represented here. There you have it. It's almost done. Okay, notice the graph very slowly. It's actually doing a lot of calculations. Okay, it's doing a bunch of average rates of change between really, really closely spaced points. All right, so this is a rough idea of what the derivative graph would look like. Notice that this piece up here is the original function, and it is fairly flat. And then it starts to get steeper and steeper negative style. And then it goes really steep and falls into the origin. So if you thought about the way the tangent lines looked, they had fairly horizontal slope, and then they dropped off and got steeper and steeper negative, and then eventually, as you got near the origin, the tangent line was extremely steep, vertically speaking, and negatively sloped. So we're talking about tangent lines very, very steep and sloped negative. So that is why our graph for the derivative dropped to negative infinity right there on the left. Okay, and then the same thing on the right, except it's the other direction. As you come out of the origin, these tangent lines starting out are very, very steep and positively sloped. So what happens is your derivative is very, very high. That means it's very steep. And then as you go out toward the right, these tangent lines get more and more shallow, getting closer and closer to zero. See? So that means that your derivative is going to come closer and closer to the x-axis. So I exaggerated it. It's really actually very tightly spaced. It's all real close. If you need to zoom in, you can see it better. But that's what it looks like. Notice that LHD and RHD are different. LHD is negative infinity and RHD is positive infinity. So we would call this a cusp on the black graph. So the graph here has a cusp, not a corner. So differing one-sided derivatives and infinite derivatives in nature. Okay, so let's go back to here and we can just move on. That's the end.